So lesson 13 is on the electromagnetic wave calculations. We're going to discuss what waves are, what the wavelength formula is, photoelectric effect, and Planck's formula. So energy waves are described as wavelength, amplitude, or frequency. And wavelength is the lambda, which represents the length of a complete wave in a meter. So if you notice, it goes from crest to crest. Crest is the peaks of what you see underneath. The amplitude, which is described by a capital A, is the distance from the origin to the crest or to the trough.
The bigger your amplitude, the more energy or the louder something is.
Right. And then finally, frequency, which is nu. I know it looks like a V, but it's the Greek lowercase nu. It represents the number of waves in a set time, and they describe this in terms of hertz or per second, which is seconds to the -1. So if you notice how many times we can calculate from crest to crest, there's 2 of them. So this would have 2 hertz.
So the wave equation is very simple. C is equal to lambda V.
Nu.
Or nu.
Not V.
Not V?
No.
Nu? Like not old, but new?
Yeah.
Okay.
And
And C is 3.00 times 10 to the 8th meters per second. C, if you don't know this, is the speed of light. That's actually how fast a photon travels through a vacuum. Lambda is the wavelength, which, pay attention, is in meters. And nu is the frequency, which is represented in either hertz or per seconds. Seconds to the -1 power. So here's a question. What is the frequency of a photon with a wavelength of 650 nanometers?
That's a great question.
Well, step by step. That's the first thing we got to do.
So first we're going to convert our nanometers to meters. Then we're going to plug values into the wave equation. And then we are going to use correct units.
We're looking for frequency, so what should our unit be?
Our frequency will end up being hertz or per seconds.
All right, so step 1. Let's convert, table C on its side. Oh, this is easy. 650 nanometers to meters. Moving 9 places to the left, I see. Therefore, you should have 6.50 times 10 to the -7. If you wanted to write that entire number out, that's on you. Hope you don't forget any of those zeros. What's the second thing we did?
So the second thing we do is plug in the numbers into our lovely equation. And C, which is always going to be 3.00 times 10 to the 8th meters per second, is a given number, so they don't have to give it to you. Then you add the 6.50 times 10 to the -7th, and you're multiplying it by nu. Okay, now, according to the rules of math, we got to get nu by itself. And we end up doing the speed of light divided by our wavelength. Finally, coming up with an answer of 4.6 times 10 to the 14th hertz, or 4.6 times 10 to the 14th seconds to the -1.
So let's try another problem. Using the same values for C is equal to lambda nu. Let's try another problem. So using the same formula, we are going to look at this radio station, WGBB, on Long Island, and it's broadcasting an AM signal at a frequency of 1,250 kilohertz. So we want to find the wavelength of this radio wave. So the only piece of data we actually have is 1,250 kilohertz. Is that an acceptable unit that we can use?
No, because it's in kilohertz.
So we have to convert it to
Hertz.
Because if you forgot, just look in the bottom left. It says your mu has to be hertz or per seconds.
Yeah.
So step 1, using table C, we convert. We're going to the right 3 places from kilo to our base. So you should get 1.25 times 10 to the 6 hertz.
Plug it in and solve. If you do this right, you're going to do speed of light divided by frequency, and you end up with 240 meters.
That means a radio wave from crest to crest, as being signaled from this radio station, is 240 meters long. That's very big, and that's also why radio waves can reach very far distances. So Albert Einstein in 1905 came up with this idea called the photoelectric effect. And he was stating that This occurs when matter emits electrons upon exposure to electromagnetic radiation, such as photons of light. And each quantum of light we call the Planck's constant, which means that Planck's constant is the sufficient energy to eject a single electron. So every photon that hits a piece of metal and you see it being shiny, you're actually looking at that energy being transmitted outwards as light.
Project about the photoelectric effect and how the photoelectric effect works. I've been wanting to do this for a while, and while working on larger projects, now was a good time. We start with an electroscope. This is an easy to make one, and one of my very first videos shows how you can make it yourself. I bought some zinc from an online science store. Just search for zinc metal electrode. Clean the oxide layer off the zinc using some steel wool or fine sandpaper. Place the zinc on top, such that it's in electrical contact with the electroscope's terminal. Then charge up a glass with a positive charge. I'm doing that using the Photoelectric Effect by rubbing it with a piece of vinyl cut from leftover window blinds. The cleaner the glass is, the better this works. Then bring that glass near the zinc, but not touching it. Touch any of the metal on the electroscope with your finger, and, with the glass still near the zinc, remove your finger. Notice what happens to the aluminum foil leaves down here when I pull the glass away. They spread apart. Next, get a black light, which is a fluorescent lamp that gives off ultraviolet light. This one came from Home Depot a number of years ago. There are also incandescent light bulbs sold as black lights, but they don't seem to work. You've probably seen these black lights before. They're popular at parties for making things glow, even spooky things. With the electroscope raised a bit to be closer to the ultraviolet light, I let the ultraviolet light shine onto the zinc. Watch what happens to the leaves down here. With this fluorescent lamp, it happens slowly, since there aren't a lot of photons to start with. But this is how much the leaves moved back together after 2 minutes and 26 seconds. How does the photoelectric effect work? When a photon of ultraviolet light arrives at a zinc atom, that gives enough energy for an electron to break free and fly away. In the electroscope, the only reason the leaves are spread apart is because we charged it with more negative electrons than positive protons. So the leaves are negatively charged and repel each other. But as we lose electrons due to the photoelectric effect, there are fewer and fewer electrons overall, including at the leaves. They're becoming less and less negatively charged, and so they gradually come together. Here's the same experiment, but with the ultraviolet light not turned on. And here it is again 6 minutes later, no noticeable change. So use an ultraviolet light.
So again, with his idea of the photoelectric effect and the wave-particle duality talked about de Broglie, he concluded that light has both properties of waves and particles. As they're going straight, they're also bouncing back and forth. And photons have this amount of energy. All photons, all light, carries what we call quantum energy.
Max Planck came up with his theory by seeing the emission of light from hot objects. So energy is emitted and absorbed only in small discrete packets called quanta. And quanta is the minimum amount of energy change. So quanta is to energy like the word atom is to matter. Now if you look at this picture, you can also see how the electrons are in their excited state at the moment.
So that horseshoe obviously was heated somewhere and it started to glow. That glowing is showing that the metal is being excited. Now, all that energy it took to get that piece of metal to that very specific temperature to make it glow, Max Planck observed and said, if I can see this glow, and using the photoelectronic effect that Albert Einstein discussed, he's basically saying that all that energy that was being stored into the metal is now being released as light, which he's calling quanta.
Where did quantum theory come from? It started not as a crazy idea, but with a light bulb. In the early 1890s, the German Bureau of Standards asked Max Planck how to make light bulbs more efficient, so that they would give out the maximum light for the least electrical power. The first task Planck faced was to predict how much light a hot filament gives off. He knew that light consists of electromagnetic waves, with different colors of light carried by different frequency waves. The problem was to ensure that as much light as possible was given off by visible waves rather than ultraviolet or infrared. He tried to work out how much light of each color a hot object emits, but his predictions based on electromagnetic theory kept disagreeing with experiments. Instead, in what he later called an act of despair, he threw the existing theory out the window and worked backwards from experimental measurements. The data pointed him to a new rule of physics. Light waves carry energy only in packets, with high-frequency light consisting of large packets of energy and low-frequency light consisting of small packets of energy. The idea that light comes in packets, or quanta, may sound crazy, and it was at the time, but Einstein soon related it to a much more familiar problem: sharing. If you want to make a kid happy, give them a cookie. But if there are two kids and you only have one cookie, you'll only be able to cheer them up half as much. And if there are 4 or 8 or 1,600,000, you're not going to make them very happy at all if they have to share one cookie between them. In fact, if you have a room with infinitely many kids but not infinitely many cookies, if you share the cookies evenly, each kid will only get an infinitesimally small crumb, and none of them will be cheered up. And they'll still eat all your cookies. The difference between light waves and kids is that you can't actually have infinitely many kids in a room, but because light waves come in all sizes, you can have arbitrarily small light waves, so you can fit infinitely many into a room. And then the light waves would consume all your cookies. I mean, energy. In fact, all these infinitesimal waves together would have an infinite capacity to absorb energy, and they'd suck all the heat out of anything you put in the room, instantly freezing the tea in your cup, or the sun, or even a supernova. Luckily, the universe doesn't work that way, because, as Planck guessed, the tiny high-frequency waves can only carry away energy in huge packets. They're like fussy kids who'll only accept exactly 37 cookies or 162,000 cookies, no more and no less. Because they're so picky, the high-frequency waves lose out, and most of the energy is carried away in lower frequency packets that are willing to take an equal share. This common average energy that the packets carry is in fact what we mean by temperature. So a higher temperature just means higher average energy, and thus by Planck's rule, a higher frequency of light emitted. That's why as an object gets hotter, it glows, first infrared, then red, yellow, white, hotter and hotter towards blue, violet, ultraviolet, and so on. Specifically, Planck's quantum theory of fussy light tells us that light bulb filaments should be heated to a temperature of about 3,200 Kelvin to ensure that most of the energy is emitted as visible waves. Much hotter, and we'd start tanning from the ultraviolet light. Actually, quantum physics has been staring us in the face since long before light bulbs and tanning beds. Human beings have been gazing into fires for millennia, with the color of the flames spelling out quantum all along.
So Max Planck came up with this formula, and it links the amount of energy a photon carries with the frequency of its electromagnetic wave. So E, capital E, is equal to h nu, and E is equal to the energy of a photon, which is going to be in joules. H is Planck's constant, which is 6.626 times 10 to the negative 34th joules per second. And nu is again the frequency, which is represented in hertz or per seconds. So first step is let's find the energy of a 2.5 times 10 to the 14th hertz light wave. So what do we got to do?
So we're going to convert the units to base form if they are needed, just like we did in the last round. And then we're going to plug the values into the Planck's formula, and then answer should be in joules if you're looking for energy. So, plug in the numbers, 6.626 times 10 to the negative 34th, because that is a constant value. Then you're going to multiply it by 2.5 times 10 to the 14th hertz, and you end up with energy of 1.66 times 10 to the 19th joules.
This just means that this individual piece of light, this individual photon, has its own very, very, very small amount of energy. But when light ever occurs on something, it's not one photon, it's billions upon billions upon billions of them. That's why if you hang out in the sun long enough, you start to feel hot because of all the energy from the photons that are being absorbed into your body.
Right. So here we have another equation. Calculate the energy in joules of a photon for green light having a wavelength of 560 nanometers. Now here's the problem. We have, and where's the wavelength coming from, and how do we use it to find energy when what we need is frequency? So we're going to actually convert frequency using our speed of light formula, and we're going to create this new formula. Energy is equal to h lambda divided by c, which is the speed of light. Now we can convert the nanometers into meters using table C. Okay, so after you've plugged everything in, just now you have to find energy.
We're going to be checking class to see if you got this right.